My name is G, and I'm a robotics student here at the University of Maryland. This semester, I took the course ENPM809T Autonomous Robot. This is a hands-on course, and throughout the semester, we get to build and program our own autonomous robot. The finished product is this guy right here. To complete this course, our robot has to finish the final grand challenge, which is to collect a total of 9 different blocks from a colored environment and deliver them to a construction zone. The robot has to collect these blocks in a particular sequence according to their color. Specifically, the robot has to first collect a red block, and then followed by a green block, and then followed by a blue block. And the robot has to repeat this a total of 3 times. What makes this even more difficult is that there are blocks of other colors in the same environment. So this poses a lot of challenge for the control and perception of the robot. To complete this task, I wrote more than 2,000 lines of code, and I implemented more than 5 custom classes in Python. Next, I'm more than excited to share with you my journey through this course. Let's start with the robot assembly. I would like to begin by showing you the main components of the robot. First, we have the Raspberry Pi, which provides the major onboard computing power. Second, we have the Pi camera mounted in the front that serves as the eye of the robot. Third, we have the ultrasonic sensor, which measures the distance to any potential obstacles in the front. Next, we have the gripper, which the robot uses to retrieve the color blocks. Now let's take a look from a different angle. In the back, we have the IMU, which we rely on for the yaw angle of the robot, and the Arduino Nano that interfaces with it. Next, we have the motor driver, which we use to control the left and right wheel speed. Last but not the least, we have the battery packs that power the Raspberry Pi and then the motors. And these are the main components of this robot. Now let's jump back in time. I want to show you the process of building this robot. We began assembling the robot in class, and here you can see me putting together the chassis of the robot, as well as mounting the motors, the wheels, and the battery pack. And all these constitute the foundation of our robot. Next, we put on more electronics such as the Raspberry Pi, as well as different sensors. But to properly shield these electronics, I use 3D printing to make enclosures from PLA. And here you can see my own 3D printer in action. This is the finished product of this particular batch of prints. And you can see the spacer for the motor driver on the lower left, as well as the casing for the camera on the right. Some of the designs are downloaded from websites such as Thingiverse, but I also make custom ones. For example, this one for the ultrasonic sensor, using Fusion 360, my go-to CAD software. And here is the finished product, and you can see it fits the sensor very nicely. Here you can see me putting the Pi and the camera in their casings, although the camera mount design actually changed later on. Next, we proceeded by mounting and wiring the motor driver. And here you can also see the mounted Pi as well as the ultrasonic sensor. And also we have 2 additional pieces that holds the battery pack. Next, we install the gripper, and here you can see me testing the opening and closing of the gripper. And finally, the IMU and Arduino Nano were mounted and wired. And by now we have a fully assembled robot. This has been a really fun process, and I learned the basic electronics of our robot. And I used my CAD skills to not only make the robot look nice, but also robust to any potential late-night coffee spills. Next, we began programming the brain of the robot. But first, we need to tackle the problem of motion control. Our robot has 2 major actions. The first is to move in a straight line, and the second is to pivot by a certain angle. To make the robot move in a straight line, we use this particular control law. Our robot has 2 control inputs, UL and UR, and they are for the left and right wheel speed. We constrain their summation to be a constant, but their difference is modulated by the output of two PID controllers based on the encoder error as well as the yaw angle error. This controller maintains a constant forward speed, but also keeps the robot in a straight line. Here's a demonstration of this controller driving the robot forward for about 50 centimeters. Next, I tackle the controller for pivoting by a certain angle. I use the controller I'll show here on the screen, and the wheel speed is the output of the PID controller based on the heading angle error. Combined with the previous controller, I made the robot follow a rectangular trajectory, and here you can see the robot following the path very faithfully. The video is sped up by 100%. Now that our robot can move around with these controllers, our next job is to make the robot able to perceive the environment using its camera. We mainly used OpenCV for various perception tasks. At the beginning of the semester, we started with simple object tracking using color masking. And here, this is an example of tracking the green signal light. Next, we move on to tracking something more complex, such as the corners of a green arrow. And here, we can identify the direction it is pointing to. This turns out to be something important for the path planning algorithm later on. Now, the grand challenge needs us to identify blocks of different color. So we designed specific color masking in the HSV channel such that we can separate these blocks. And here is an example of separating the blue block from the background. We also designed different vision-based controls. And for example, here, the robot can center the red block in the field of view. Now that our robot can successfully identify these blocks, the remaining question is how to get to these blocks from a distance. Now also remember there are other blocks in the same area, so we need to find out ways around these non-target blocks. And this is where the path planning kicks in. Now let's consider this situation where the robot needs to get to the red block without hitting the green or the yellow one. So first, it needs to figure out where these blocks are in relationship to its own position. And to do so, we apply the concept of homography. What essentially means is that if we have a set of points on a plane and we take a picture of them, where these points appear in the image is linearly related to their physical locations. And therefore, if we know this relationship, we can recover their physical positions based on where they appear in the image. Now, we know that the points where these blocks are in contact with the floor satisfy the homography. And therefore, we just need to find the homography relationship. And to do so, I did some calibration where I put pieces of paper in front of the camera and I measured the corners of this paper in relationship to the robot. And through some linear algebra, I can recover the homography, which will actually give me a top view of the scene as shown here. Next, to find the points on the floor, we use the same corner detection algorithm developed previously. And we only need to keep the lower points as they are in contact with the floor. Now, with the real-world coordinates of the block, we can use the path planning algorithm to find the desired path to the target block. Let's now go back to our first situation and see all the components working together. Here's the robot's view of the scene, and it has correctly identified the color and the locations of these blocks. The white lines are the generated path. Now let's further look under the hood and see how the planning algorithm finds the path. As you can see, the planner builds a roadmap and makes sure that the path does not cross the other blocks by offsetting a certain radius around them. The final path is generated by the A-star search algorithm and further trimmed to reduce the number of maneuvers needed. Now let's see the robot carry out the path. The video is sped up by 100%. As you can see, the robot retrieved the block successfully as intended. Finally, our robot is ready for the grand challenge. This is the actual arena for the final grand challenge. Again, the robot has to collect and deliver red, green, and blue blocks in that particular order to the construction zone, which is in the upper left corner. And this process is repeated 3 times. Here's the time lapse of the robot completing the grand challenge, and you can see the robot's view in the lower left corner. Now the robot is going for the first green block, and you can see the past planning kicking in when the robot goes around the red block in its way. The rest of the blocks did not pose too many challenges, except for the last one. Now you can see the robot going for the last blue block, but somehow it got a little too close and lost sight of it for a second, but still managed to retrieve it at the end. The robot actually completed 2 runs of the grand challenge, and the trajectory is mapped by the odometry shown here. In both runs, the robot retrieved all 9 blocks under 8 minutes. This shows that our algorithm is highly robust and efficient. Overall, I'm very happy with these results. And here, these are some of the past planning photos the robot generated during the actual grand challenge run. And that wraps up our journey through this semester, building an autonomous robot from scratch. And I'm truly grateful to everyone who helped me throughout the process. And thank you for your attention.